So I'm going to present ADSNARK, narrowly practical and privacy-preserving proofs on authenticated data, and this is joint work with Michael Bacchus, Manuel Barbosa, and Rafael Rashuk. So I'd like to start by giving you one of the motivations of this work. So this is a piece of news that appeared a few days after the conference deadline, and what it's saying is that Generali, which is an insurance company in Germany, is introducing this electronic patient. So what does it mean? So basically, these insurance companies wants to introduce a model in which it's encouraging its patients to wear biosensors that are collecting health data, and then if this health data is given to the company, and the company is happy like that, you prove that you're healthy, then it's going to give you a discount on the premium. So if this is the model, we can make some observations about what's going on. So the first observation is that what the company is actually interested in this model is to know whether, for example, you are healthy or not. So more generally, it wants to have aggregations of the original data that is collected by the biosensor. On the other hand, if this is really what they want, then what the patient can do might compute this aggregation by itself and give this result to the company. Okay, so but there are some security concerns here. The first one is that from the point of view of the patient wants to be sure that if this aggregation is given to the company, this aggregation should not leak more information than its value. So in particular, it should not leak information about the original data. And from the point of view of the company wants to be sure that the result, this aggregation that is computed, is really correct, and the patients are not trying to cheat. And finally, something which is also important is that the company wants to be sure that the data on which the aggregation is computed is really the one collected by the biosensor. So it's not, and it is not being tampered with. So if you're familiar with this security concern, you might already realize that the first two properties are something which is typically addressed by the cryptographic notion of zero-knowledge proofs, whereas if we care about authenticity of data, we know that digital signatures can provide some solution. So what we are studying in this work is basically to look at the combination of these two properties, and in particular to obtain a good combination in an efficient way. So let me be slightly more formal. So in this work, we consider the following three-party application scenario. So in this scenario, there are three parties. One is a trusted source, and the trusted source is collecting and authenticating some piece of information X, and this information is given to another party, which is the data owner. Okay, so the data owner is really the one that owns the data, and what he wants to do is to give this some partial information about this data to the service provider. And the service provider, on the other end, does not trust the data owner to correctly compute this aggregation f of x. And it's important that we only provide the service if it's convinced about that. So in terms of properties, basically, we have that the trusted source is defined legitimacy, so what is like a legitimate data. The data owner is the one that wants privacy, and the service provider wants integrity. So the basic idea that we are going to push in this work is to have the data owner produce some proof which is privacy preserving. So it should prove to the service provider that this f of x is correct, and it should not leak any more information about x. And also here, it's important that the service provider should also be convinced that x has been authenticated by the trusted source. So we also want to ask whether this model makes sense in practice. So we have some examples. So one is this health risk assessment that I just described you in a couple of slides before. So very briefly, the biosensor is the one that collects the data and represents the trusted source. The customer of the company is the data owner, and the insurance company is basically the service provider. Another example that fits this model is smart metering. So I don't have time to go into the details, but the very brief idea is that there is a smart meter that collects fine-grained and periodical energy consumption information, and is giving this information to an household, which basically represents the data owner. And the energy company is the one who receives the bill. So you can see the bill as an aggregation of this data, and he wants to be convinced that the bill is correct while not learning information about the individual measurements. And many more examples are available. So in the paper, we discuss many more of this, such as pay-as-you-drive insurances, loyalty cards, or health statistics. OK, so what do we know in previous work about this model? So these problems have been addressed by several works. So I mean, I could fill in an entire slide with all citations, but I want to highlight some of them. So in general, the idea of privacy-preserving data processing have been addressed, for example, by the ZQL compiler that has been proposed at Usenix 2013. And also more specific works have, for example, addressed the problem of privacy-preserving smart metering. And the problem of making proofs about authenticated data is also the goal of the notion of homomorphic signatures or homomorphic message authenticators. And finally, there is a lot of work, especially in the recent years, about succinct and efficient general-purpose zero-knowledge proofs, such as the work that we have seen in the previous talk. So what was lacking in this previous work, if we consider our problem? So the observation is that previous solutions were lacking at least one of these three features. So the first feature that we want is that we want a solution which is suitable for this three-party model, in the sense that you can deal with proofs on authenticated data. It must be general, so we want some solution that it does not work only for some computation. It should work for any arbitrary computation, and it should be scalable, in the sense that it should degrade very nicely with an increasing complexity of the computation. And the observation here is that, unfortunately, none of the solutions were achieving all these three properties altogether. So just to give you an example, so if you take one of the very efficient non-interactive zero-knowledge proofs, they are general, they are scalable, but as soon as you add you want to deal with proofs on authenticated data, they might not scale so well. So the goal of this work is to basically provide a solution that can satisfy all these three features altogether. So the contribution of this work is to define a notion of that we call zero-knowledge ADSNARKs, that stands for succinct non-interactive arguments of knowledge on authenticated data. So you can see it as an extension of SNARKs to this specific three-party application scenario. And then what we did is to formalize this notion. Then we show a generic construction that just uses any zero-knowledge SNARK and the digital signature to achieve this notion. And here the observation is that, unfortunately, this is not always very efficient in practice. And motivated by this, we propose our new protocol, which we call ADSNARK, whose main benefit is to be as efficient as state-of-the-art zero-knowledge SNARKs. And in addition, it provides proofs on authenticated data. Okay, so in the next talk, I will first briefly describe what is the generic construction. I will discuss why it is not so efficient, and then I will describe our solution. So what is the main idea? So the idea of the generic construction is very simple. So what we're going to use is a zero-knowledge SNARK. So we can make zero-knowledge proofs that are succinct and a digital signature. Using this, so what we want to prove is, for example, that you have some, we want to prove arithmetic circuit satisfiability. So we want to prove that this circuit C is satisfied for some statement X and the witness W, and X is what is digitally signed. So what's the basic idea? So the trusted source is going just to sign the data using a digital signature. And the proof, what it's going to do is to make a proof that this circuit is satisfied, and for every element of the statement X, there exists a valid signature. So essentially, technically, what you're going to prove is another circuit C prime that embeds circuit signature verification inside. So how about the efficiency of this solution? So here the observation is that what we are actually proving is C prime, it's not C, right? And the C prime is another circuit that includes signature verification inside. And by looking at the way we could encode this, basically what we have to do is to encode the verification algorithm of a signature scheme in the circuit. And with a rough estimation, this costs at least 1,000 multiplications per input, and which is a significant slowdown, especially for the prover. So then the question we asked ourselves was, is this like augmenting the circuit really necessary, or there is some other way we can achieve the same goal in a more efficient way? And that's where our solution stands. So the way we built our protocol was to start from state-of-the-art zero-knowledge SNARKs, in particular, those schemes based on quadratic arithmetic programs such as Pinocchio, its optimizations. And then we embedded some novel homomorphic message authentication technique with some property of randomization that I'm going to quickly describe. So what's the basic idea we got to this construction? So if you look at the regular SNARK, when you have to verify the verification algorithm, looks like the one on the slide. So you verify with respect to some verification key, you know the input X, and you have the proof pi. And this is possible because in plain zero-knowledge SNARK, you do know X. But it's not the case in ADSNARK, because we said that X is private. So actually, in that algorithm, you don't know X. So assume that we want to use such an algorithm. So our first idea was, can we outsource like this, the verification algorithm itself to the prover, because the prover knows X, so he might run this for us. So let me be more technical now. So in the slides, you see that there is a verification algorithm of the optimization of the Pinocchio scheme that has been proposed at USENIX 2014 by Benzosson et al. In red, I'm highlighting the part of the verification algorithm that is related to with the input X. So in particular, what is important here is that the verification algorithm is computing some value which we call VKX, which is some linear function over these inputs. Now our idea is to move this computation to the prover, but since the prover might cheat, we want to enforce the prover to be correct, and also recall that here the prover should make a proof that this holds for some authenticated X. So the way we solve this is to make this computation provable using another proof system, which is an homomorphic message authentication scheme. And using this, the prover will basically compute VKX for us and make a proof about its correctness. So there are some technicalities that we had to face to reach this solution. The first one is that the coefficients of this computation are not integers, but are group elements. And this is not something that was possible to do with previous homomorphic max. But the most critical and interesting issue that we had to solve was that if you give VKX by itself, this may reveal information about the input. So what we did is to provide a randomized version of it and to develop a technique that can deal with for homomorphic map for randomized computations. So let me give you some numbers about the impact of this of our solution. So we implemented ADSNARK as an extension of the libsnark library, and a benefit of this is that, for example, we can reuse all the existing work, for example, on the tool, compiler tool chain that is available for the library. And additional cryptographic components, we took them from another framework, the Supercop framework for digital signatures and pseudo-random functions. And what we measured is how the system scales with respect to general circuits of growing sizes and a growing number of inputs, as well as circuits for some specific applications, such as smart metering. So let me show you some numbers. So here I'm showing you the performance for the case of constraint systems of 50,000 constraints and a varying number of inputs from 100 to 1,000. And in purple, so you see PGHR, which is the Pinocchio protocol, in particular this optimization that is in the Usenix paper. And this is like a plain zero-knowledge snark. So it does not give you this security, this guarantee against authenticated inputs. In green, there is the generic solution that is implemented on top of the Pinocchio protocol. And here we use an estimation of adding an overhead of 1,000 multiplication gates per input. And finally, ADSNARK in blue is our protocol. And so in the first graph, I'm showing the running time of the key generation algorithm. And you see that already, like, the generic solution is not scaling very well for a growing number of inputs. And a similar behavior happens with the proof algorithm. So here, basically, what's happening is that our solution is basically performing as good as the plain zero-knowledge snark that does not give you any authenticated correctness guarantee. And finally, what I want to show is the performance of verification algorithm. So here we have something more interesting. So in ADSNARK, we have two modes of verification. We have a secret key mode that works like verifying a MAC, and a public key mode. When you use secret key verification, basically we can perform almost the same as the other schemes. When we switch to public key verification, then the running time of our verification algorithm is growing with the number of inputs. So this is not good in terms of scalability, but still what we observe, and this is the good news, is that still we remain in what we can call the realm of practicality, because even if we have this non-scalability, that we are still below 1 second to verify. A similar thing happened with the size of the proof, so that in the public key case, the proof is no longer constant size, but the overhead is really small. So it's like 100, roughly 100 bytes per input. So in some sense, this is telling that it's like we shifted some work to the verifier, and we are adding to the verifier some very little work, because he was already paying very, very little, but we can save a lot of work for the prover. So I'd like to conclude. So in this work, we consider the three-party model for the case of zero-knowledge, general purpose zero-knowledge proofs. And our main contribution is this new scheme called ADSNARK, whose benefit is to run as efficient as plain zero-knowledge snark, but on top of this, it additionally provides integrity for authenticated inputs. And our work leaves some open questions, such as, for example, how to achieve publicly verifiable constant size proofs. So I think it's an interesting direction in order to further optimize this solution. And also, it's not clear yet if all these techniques would extend if we move to the RAM computation model. And that concludes my talk, and I'll be happy to pick questions if you have.
we have a minute or two for questions if anybody has one. So I guess I had kind of a small question. Maybe it's just a verification of the motivation, but how does this compare to just having the trusted device do all of the computation internally?
Yeah, that's a good question. So, I mean, that might be a solution, but then in that case, you are assuming that this trusted device is performing a lot of computation inside. So in this case, we are using the device in a very, very little way. So the only thing he has to do is to just stream data, it authenticates the data. And also, the device itself must not be online when the proof must be generated. So you can even throw it away in some sense.
And what's the burden on the device has to encrypt the data, right?
He has just to authenticate.
Oh, just to authenticate.
Yes. So, I mean, it's like generating a digital signature.
Okay, no more expensive than this.
Yes.
Cool. Okay, well, if there's no questions from the floor, then we'll thank Dario one more time.